It's crazy to think about all the computing power behind these like super advanced AIs these days.
Yeah, it's mind-blowing, right?
Definitely mind blowing. Like we're seeing these huge language models, LLMs,
LLMs, yeah.
doing all these incredible things like complex reasoning and coding, but they just eat up so much processing power, especially, when they're actually generating text during inference time. I mean, it's a lot.
You're right. It's a crucial aspect of this whole field.
I think a lot of people are trying to keep up with all the latest developments, but maybe they don't like have a PhD in neural networks.
Yeah, totally.
They just want a way to like grasp the basics of these models.
Get to the core
Yeah,
ideas.
exactly. So that's what we're going to try and do today. So we're diving into xLSTM-7B. It's a 7 billion parameter language model that's getting quite a bit of attention. It's all about speed and efficiency, and everyone wants a piece of that.
For sure.
We have the research paper right here, xLSTM-7B, a recurrent LLM for fast and efficient inference. I've also got my own notes.
Awesome.
Our mission today is to help you understand what makes xLSTM-7B so special, especially when you compare it to like those big transformer models.
Right.
We're going to look at the architecture, why it's so efficient, and what it could mean for, using LLMs in the future.
Yeah, applications, exciting stuff.
We're aiming for more of a, kind of an academic explanation. So we're going to focus on the real technical details,
Yeah, the core points.
the core points. So, what's really interesting here is the whole idea behind the paper. They're saying that a lot of the recent breakthroughs in LLMs have been kind of like, trading off performance for compute power during
The
inference.
trade-off.
It's a trade-off. Like they point to these methods where the model tries out tons of solutions to get better at reasoning and math problems, and they cite work from Yao et al., Hao et al., and Guan et al. You've probably seen this in models like, OpenAI's O11 and DeepSeek R1.
Yeah, those are great examples.
They're basically doing like a ton of internal trial and error while they're generating text, right?
Exactly. It's like exploring a bunch of possible answers.
They're exploring a bigger solution space at test time
That's a good way to put it.
to get better results, but it comes at a cost, right?
Right. Computationally, it's expensive.
Yeah, so it's all about finding a balance.
Exactly, and that's what xLSTM-7B is all about. Can we do this without all the extra computation?
Can we get those great results without needing a supercomputer?
Exactly.
The paper talks about XLSTM as part of this like wave of new architectures, linear recurrent neural gating mechanisms.
Right, like moving away from transformers.
Moving away from transformers, they mentioned other examples too, like GLA, Mamba, RWKV, and RetNet.
Yep, all exploring efficient ways to process sequential data.
So XLSTM is part of this bigger trend.
It is.
Now, let's get specific. What makes the architecture of XLSTM-7B so efficient, especially when we compare it to transformers?
Okay, so, transformers are powerful, but the self-attention mechanism, well, it has this problem. The computation goes up quadratically with the length of the input text.
Quadratically, so that means,
So if you, like, double the text you give it, the computation for attention quadruples.
that seems like a problem, especially with longer texts.
Yeah, it can be a huge bottleneck.
A huge bottleneck. So how is XLSTM different?
xLSTM is a recurrent model, so its computation grows linearly with the sequence length.
Linearly meaning
Each new element in the sequence adds a fixed amount of computation.
it's like processing the text step by step.
Yeah, exactly.
And that makes it much more efficient, especially with longer texts.
Right, especially with those long sequences.
Okay, cool. So what about memory usage during inference?
Ah, that's another key point. xLSTM uses a constant amount of memory during inference.
Constant memory. How did that work?
Okay, think about transformers. They use this thing called a KV cache, stands for key value cache. It stores information from earlier parts of the sequence.
Okay, I kind of remember that.
But the problem is this cache grows linearly with the sequence length. So with long texts, you can end up needing a ton of GPU memory.
It just keeps growing and growing.
Exactly. xLSTM, on the other hand, keeps its memory state fixed.
So no matter how long the text is, the memory stays the same.
Exactly.
That's amazing. So what are the implications of that? What does that mean for actually using the model?
Well, for one, it means you can do more of that test time compute we talked about. You can explore more solutions without running out of memory.
Right, because the memory isn't growing out of control.
Exactly. And it also opens up the possibility of running these models on devices with less memory, like edge devices.
Oh yeah, that's a game changer.
Right. Imagine you could have a local AI assistant that can remember a long conversation.
Without needing a giant server farm to power it.
Exactly. And with xLSTM, it's possible the memory usage is predictable and stable.
Okay, that's super interesting. Now, the name XLSTM-7B tells us it has 7 billion parameters.
Yeah, 7B, that's big.
The paper mentions that earlier xLSTM models were, like, smaller. Why was scaling to 7B so important?
Good question. The earlier models were around 1.3 billion parameters. They showed promise, but there was this like uncertainty. Could xLSTM really compete with transformers at these larger scales?
The scales where transformers really start to shine,
Exactly. Could it learn from massive data sets and get those amazing emergent properties?
right? Because those properties are often tied to scale.
They are.
So xLSTM-7B was a way to answer that question.
Absolutely a big test.
So how did they actually do it? They scale it up to 7 billion.
So they went all out. They trained xLSTM-7B on a massive data set of 2.3 trillion tokens.
Trillion. Wow.
From the DCLM dataset, they used a context length of 8,192 tokens and a whopping 128 H100 GPUs.
128 GPUs, that's serious hardware.
They needed it, and it wasn't just about making it bigger, they also refined the original xLSTM architecture.
So they optimized it for training.
Exactly, they wanted to make it more efficient and stable, but without sacrificing performance.
That's a tough balance.
It is, but they managed it.
Okay, so what specific optimizations did they make? I know the paper talks about an optimized MLSTM block.
Right, that's key. So earlier xLSTM models used this pre-up projection block. Basically, the MLSTM cell, which sometimes had channel-wise convolutions.
Channel-wise convolutions, what are those?
They're a way for the model to look at different features, different channels of the data at each step. So the MLSTM was sandwiched between layers that increased and then decreased the dimensionality of the data.
So it was working in a higher dimensional space.
Right, and that's one of the big changes in xLSTM-7B. They switched to a post-up projection block, more like a transformer block.
More like a transformer, okay.
Now, the MLSTM operates in the model's embedding dimension.
Lower dimensional, more efficient.
Much more efficient, less computation, less memory usage.
So it's doing more with less.
Exactly. And they didn't stop there. They added position-wise feed-forward MLP layers with SwigglU activation after each MLSTM layer.
Again, like a transformer.
Yeah, taking inspiration from transformers, this increases the proportion of the computation done by these super efficient linear layers.
The kind of operations that GPUs excel at.
Exactly. Matrix multiplications, GPUs, love those. The paper even has figures, figure 1 and 8, that show this new block structure.
Oh, cool. I'll have to check those out.
They really highlight how the information flow is optimized.
So it's like they streamlined the whole process.
They did.
What other changes did they make within the block?
Well, they also got rid of some things that weren't really helping, like those channel-wise convolutions we talked about and learnable skip connections.
So they simplified the design.
Yeah, which made the GPU utilization much better. Less overhead, more focus on those core linear algebra operations.
Makes sense. Any other changes?
Oh yeah, they also changed how they handle the query, key, and value projections. Instead of using block-wise projections, they went with dense linear layers.
More efficient linear layers?
Again, the goal is to use those tensor cores on the GPUs as much as possible. They're designed for matrix multiplications.
Oh, I remember those. They're like specialized hardware.
Right, they're built for speed. And one final optimization within the block, the pre-activations for the gates, the input and forget gates that control information flow in the MLSTM, they're now calculated separately for each head.
For each head. Okay, so remind me, what are heads again?
The multi-head mechanism. It's like letting the model look at the data through multiple lenses at the same time.
Oh, right. I remember.
So by computing these gate activations independently for each head,
They can work in parallel.
they can work in parallel. That's especially helpful when you're training on multiple GPUs, less communication overhead.
Okay, so it's all about making things more efficient.
It is, and the results speak for themselves. They got a 2x to 4x boost in token throughput compared to the old xLSTM with the same level of performance.
That's huge. That's really impressive.
It is a major efficiency win.
Now let's talk about these fused generation kernels.
Right, another key optimization for inference speed.
So what are they and why are they so important?
When the model is generating text, token by token, the MLSTM cell has to do a bunch of calculations. It's all detailed in equations 1 to 9 in the paper.
A lot of equations?
Lots of equations. In a simple implementation, each operation would be a separate kernel on the GPU.
Okay, and that's not ideal.
Not really. Launching kernels takes time, and you often have to store intermediate results in GPU memory, which is slow. Fused kernels fix that. They combine multiple operations into a single kernel.
So doing everything in one go.
Yeah, exactly. All the intermediate data stays on the GPU's fast compute units. No more waiting for memory access.
Much faster.
Way faster. It's like optimizing the assembly line inside the GPU.
That's a great analogy. So scaling a model to 7 billion parameters is never easy, right?
Never.
I know the paper mentions some challenges with training stability. What kind of issues did they run into?
So as models get bigger, they can become unstable during training. The researchers saw these like spikes in the gradients and the loss value. It's something that's been seen in other models too, like
Like
Mamba.
growing pains?
Yeah, kind of. They think it's partly because of these outlier features, values in the model's activations that are way bigger than normal.
Like throwing a wrench in the work.
Exactly. So they had to find ways to stabilize the training.
Okay, so what did they do?
Well, first, they replaced layer norm with RMS norm at the input of each layer. It's called prenorm. Other research has shown that this helps with stability in transformers and Mamba models.
RMS norm is more robust, right?
It is, and they found that it worked for xLSTM too.
Their results are in Appendix C.2 and Figure 9.
Yep, you can see it there. RMS norm helps take the activations in check.
Okay, so RMS norm was one solution. What else?
They also use this technique called gate soft capping. Basically, they apply this function, it's equation 13 in the paper, to the pre-activations of the input and forget gates, and also to the final logits.
The logits, those
The
are...
values before the final softmax layer, yeah.
Oh, yeah, okay.
So this function limits how big these values can get. It prevents those outlier features and loss spikes.
It's like putting a cap on those values.
Exactly. A soft cap, though, they tune the parameters carefully, and Figure 10 shows how it affects the training stability.
So soft capping keeps things under control.
Yep. And the third technique they used, surprisingly effective, was negative initialization of the input gate bias.
Negative initialization, that...
They set the bias to a large negative value, like It seems simple, but it really helped reduce those gradient spikes and variance.
Wow, that's interesting.
Figure 11 shows the effect. There's even other research that explains why this works for recurrent models.
So they combine these three techniques, RMS norm, soft capping, and negative input gate bias.
And it really stabilized the training. You can see it in Figure 2. The training curves look much smoother.
Okay, so they got the model to train stably. Now, let's talk about how well it actually performs.
Let's see how it stacks up.
The paper has a bunch of benchmark results. Let's start with the Hugging Face leaderboard, those standard language understanding tasks. How does xLSTM-7B compare to other 7B models on those?
So Table 1 in the paper shows that it lands in the mid-range on the Hugging Face leaderboard V2.
Mid-range, not bad.
Not bad at all, especially considering that some of the top models were trained on way more data.
Right, data's king.
Absolutely. The authors think that with more data, maybe focusing on math and code earlier in training, xLSTM-7B could reach the top.
So it has the potential.
Definitely. It shows that it can be competitive even with this focus on efficiency.
Okay, cool. Now, one of the supposed strengths of xLSTM is handling long sequences.
Long context, right?
Right. How did it do on those long context evaluations, specifically the ruler benchmark?
The ruler benchmark tests models with context from 4K tokens all the way up to 131K tokens.
That's really long.
It is. They tested the standard xLSTM-7B and a long context version, xLSTM-7B LCTX.
LCTX for long context.
Exactly. They trained LCTX with a longer context, 32K tokens, using data from several long context datasets.
Oh, so they specifically trained it for that.
They did, and they compared it to several strong baselines.
Like what kind of baselines?
Transformer models like Llama 2 7B and Llama 3.1 8B.
Llama 2 wasn't fine-tuned for long context, right?
No, but Llama 3 was heavily. They also included state space models like Cadastral Mamba and Falcon Mamba.
Those are the efficient ones?
Yep, and other recurrent networks like RWKV5 and RWKV6.
Okay, so a good mix of models.
It was a solid comparison. So Figure 3 shows the results.
What did they find?
As expected, Llama 3 did the best overall. That long context fine-tuning really paid off.
Makes sense.
Llama 2, on the other hand, really struggled beyond its 4K training context.
It couldn't handle it.
Not really. But here's the interesting part. xLSTM-7B LCTX was competitive with the state space models and beat both RWKV models across the board.
That's pretty good.
It is. And get this, it got 20% average accuracy at 131K context, even though it was only trained up to 32K.
That's impressive. It must be compressing the information really well.
It is, especially considering it has that fixed memory state.
Unlike transformers, which just keep growing their cache.
Exactly. The authors think that with more training on longer sequences and better fine-tuning, xLSTM-7B could do even better.
So it has a lot of potential.
Huge potential for a long context.
Okay, now let's get to the speed. The paper has benchmarks on a single H100 GPU.
The real test.
The real test. Let's start with generation throughput, Figure 4. What do they find?
Figure 4 shows a big advantage of recurrent models like xLSTM. Transformer speeds drop as you increase the prefill initial input context.
Because of the quadratic scaling?
That's right, but xLSTM-7B and the Mamba models keep a pretty constant generation speed regardless of context length.
That's a win for xLSTM.
Big win for long sequences.
And the benchmarks also show that xLSTM-7B is about 50% faster than Mamba.
Yeah, much faster generation. The authors say it's because of their optimized block design.
All those optimizations paying off.
Absolutely. And at prefill 0, starting from scratch, xLSTM-7B was even faster than both Llama models.
Wow, even faster than Llama.
Yeah, really impressive.
Okay, what about generation time and memory usage during generation?
Figure 5 shows that really well. You can see the generation time going up linearly for xLSTM-7B and Mamba as the text gets longer.
Linear scaling for recurrent models?
Yep, but for transformers, it's closer to quadratic scaling.
Much steeper curve.
Yeah, and for memory usage, it's even clearer. Recurrent models stay constant. Transformers go up linearly because of the KV cache.
Llama 3 uses grouped query attention, right? Does that help?
It does a bit. The memory growth is a little slower than Llama 2, but it's still linear.
Still growing.
Yep. And you can see that xLSTM-7B has both lower memory and faster generation times than Mamba.
Again, showing the benefits of those optimizations.
Exactly. They made a big difference.
Now, for applications where speed is crucial, what about the time to first token benchmark in Figure 6?
That's a good one. It measures how long it takes to generate the first token after processing the input context.
So how responsive is the model?
Exactly. And xLSTM-7B was the fastest across all the prefill lengths they tested.
Really snappy.
Super snappy. That's huge for things like chatbots or any interactive application.
Users hate waiting.
They do. That first token time is critical.
Okay, and finally, what about prefill throughput in Figure 7?
So that measures how fast the model can process the input context before generating.
Before it starts writing, basically.
Exactly. xLSTM-7B got the highest throughput, 70% higher than Cadastral Mamba, and it stayed pretty stable regardless of context length.
So it can handle long context without slowing down.
Exactly. The Llama models, their throughput dropped as the context got longer.
Again, because of attention?
Yep, that quadratic scaling.
Okay, so xLSTM-7B looks really good in these speed tests.
Really impressive performance. The authors made some great design choices.
Now, the paper also has a section on ablation studies.
Ablation studies. Yeah.
Where they test different parts of the model.
Like what happens if we remove this or change that?
Right, to see how it affects performance. What were some of the key findings from those?
So they really wanted to make sure their design choices were valid. They did a bunch of experiments, and they're all detailed in section 3 and appendix C.2 of the paper. For example, table 2 shows that switching from the pre-up projection block to the post-up projection block gave them a huge speed up during training, 3.5x faster.
Wow, that's a lot.
It is, and the performance was almost the same.
So a big win.
Big win. They also looked at the memory state size, which is basically the number of heads in the MLSTM.
More heads, more memory.
Right. Table 3 and Figure 13 show the results. The perplexity and downstream task performance were pretty stable across different numbers of heads.
Okay, so it wasn't super sensitive to that.
Not really, but it did seem like having more heads might be better for long context tasks.
Makes sense. More memory for longer sequences.
Exactly. They also confirmed that RMS norm was better than layer norm for stability. Figure 9 shows that. And Figure 10 shows how important soft capping was. It really helped stabilize the training.
Kept those gradients under control.
It did. And finally, Figure 11 in the tables show that the negative input gate bias initialization worked really well.
Reducing those spikes.
Yep. And they also found that a learnable input gate was much better than a fixed one for long contexts.
So all these ablation studies show that their design choices were good.
They really validated their work. Solid evidence.
Okay, so to wrap up, what's the big takeaway from all of this?
I think the main point is that they successfully scaled xLSTM to 7 billion parameters and trained it on a truly massive dataset.
A testament to good engineering.
It is, and they did it while improving training stability and token throughput. It's the fastest RNN-based architecture at this scale, and it's competitive with transformers and performance.
Really impressive results.
It really is. The authors believe that xLSTM-7B is a great foundation for future work, especially for things that need fast inference.
Like all those real-time applications.
Exactly. And they've open sourced the model, the code, and the training scripts.
So other researchers can build on their work.
Absolutely. It's a great contribution to the field.
So, listener, if you're following the world of LLMs, xLSTM-7B is a big deal. It's a step towards more efficient models, especially for tasks that need speed and can handle long sequences of data. It's a real alternative to those huge transformer models that can be so demanding.
Right. It's a different approach.
And it's exciting to see what people will do with it. Now that it's open source, who knows what amazing applications will come out of it.
Yeah, the possibilities are endless.
It's a really interesting time to be in this field.
It is. So much is happening so fast.
It's hard to keep up, but hopefully this deep dive has given you a better understanding of xLSTM-7B and why it matters.
Yeah, we covered a lot of ground.
We did. We'll be back soon with more deep dives into the world of AI and machine learning. Until then, keep exploring,
Keep learning.
and we'll see you next time.